Hello guys, welcome back to my channel Gamma Digamma. So in the previous video, I believe I introduced the Dirac Delta function / distribution. In this video, I'm going to talk about some of the properties, specifically what happens when you change the argument or the input of the Dirac Delta function. So without anything to hold us back, let's get started. Before starting this discussion, I would just like to point out that just like you have operator algebra, so you have operators acting on some state, at least this is the quantum mechanics language of things. And if you want to do some operator algebra, you always make operators act on a certain state. The same way, I'm not going to treat the Dirac Delta as like a single entity, because if you remember last video, it doesn't exist mathematically, at least outside the integral that it's defined in, because it's just a divergence. So using that same idea that we need some state for operators to act on when we're doing operator algebra, for a Dirac Delta we'll be taking it inside an integral. So the first interesting case is the Dirac Delta of negative the argument. So I'm just going to write it out in the integral form, just on the top. I promised to sort of make it work on a state. In this case, it's going to be a function. So inside the integral f of t. So what I can do is the natural thing to do. Let t prime equal to negative t. So a change of variable by classic integrations, negative t minus to negative t plus dt prime delta t prime f of negative t prime, which we can sort of shift the upper and lower bound by sucking in the negative. Just becomes dt prime delta t prime f of negative t prime. And we can write this out in sort of a piecewise definition. This is going to be f of 0 when negative t plus and negative t minus contain 0. This is just the definition of the classic Dirac Delta, and 0 otherwise. Okay, this property was basically part of the previous video, so you can check that out if you don't know what's going on here. But one thing to point out is, assuming you have some interval which usually is symmetric, it's usually from negative infinity to infinity, which is symmetric. Assume you have something like this, it's negative 5 to 5, which contains 0. If you sort of change the variable, you're just going to flip the positive phi to a negative phi. So the net result is not changed because of the symmetry. And this is just the regular Dirac Delta. What if you have a slightly asymmetric interval, something like, let's see, negative 7, 0, 5, which again contains 0. You change the limits by, using this substitution. 5 becomes a negative and 7 becomes a positive. But you see, it still contains 0. The thing is, even if you have a asymmetric interval, you can convert this into a symmetric one, because notice the region from 5 to 7, integral over that of the Dirac Delta is going to be 0, because the 0 of the Dirac Delta is at t equals 0. So all the other points which do not contain t equals 0, the integral will just be 0. So we can add as many points as we want, and or reduce zeros. It's just like adding or subtracting zeros. We can convert an asymmetric interval to a symmetric one, and vice versa. And by using this property, we can see that although it's negative t plus to negative t minus, we can use this symmetry or sort of converted symmetry to get f of 0 and then have these upper and lower bounds like before, t minus 0, t plus. This is just because of the symmetry or induced symmetry as I described, 0 otherwise. And if you remember this is just the definition of the classic Dirac delta of f of t. From t minus to t plus dt Dirac delta t f of t. So you notice this symmetry going on between these guys. Dt delta of negative t, that's what this really was, f of t. Which means, since f of t was an arbitrary function, this interval was defined in both cases, which was the same. We can conclude that the delta of negative t is the delta of t, which means that the Dirac delta is even. Mathematically speaking, it's not really right to pull the Dirac delta out of this integral. I just did it because there are many physicists and engineers in my viewers who actually sort of make more sense of this stuff that's going on. Because the thing is, I could set an equalities because of this reason. Anything that behaves like a delta, a Dirac delta, inside an integral is a delta. So there's this sort of uniqueness theorem, uniqueness property that goes with this Dirac delta. Since this negative guy could, be reasoned out to just be the positive, which is itself the definition of the regular Dirac delta, we can say that this equals this. So it's because of that kind of reasoning that we can conclude the evenness or show that the Dirac delta is even. Okay, moving on. Okay, so the next property is sort of a generalization of the one we had before, delta of at. So we are basically scaling it by scalar a. Let's assume that a is positive for the moment. We can generalize a little later. So let's write this out the way we did for the previous one. Delta of at f of t. Okay, the classical idea here is to change the limits of integration, and we have, say, t minus over a, t plus over a using this substitution. dt prime f of t prime over a delta t prime divided by a, which, if you sort of write this in like a piecewise manner, is f at 0 divided by a when t minus over a and t plus over a contain 0 of the delta, which is at t equals 0, and it's 0 otherwise. This is just again using the definition of the Dirac delta for this special case. Now the thing is, assume you have a short interval from, say, negative t minus over a to 0, and then from 0 to t plus over a, and then you have the entire interval from t minus over a to t minus, and then from t plus over a to t plus. The thing is, as long as the 0 of the delta is at t equals 0, integral of the delta times some function from t plus over a to t plus is always going to be 0. Same thing with on this patch, because it does not, this sort of range does not contain t equals 0, which is the 0 of the delta, and while its definition of the delta are giving us 0. So it doesn't matter how many factors you add to your t plus over a and t minus over a, because since they're 0, it's like adding 0, which is equal to the initial thing itself. So this can be written as f of 0 over a at t minus and t plus range and 0 otherwise. This is just because we can add zeros to the initial expression of 0 to t plus. We can add this patch of t plus over a to t plus, and it won't change anything because it's like adding zeros or subtracting zeros either way. And this, believe it or not, is just integral from t minus to t plus of 1 over a dt Dirac delta of t f of t, which is 1 over a. So if we sort of write them outside the integrals for the physicists and engineers out there, 1 over a f of 0 is equal to Dirac delta of a times t, for example, which is precisely Dirac delta of t over a. Yup, this is a nice property, and if you sort of plug in negative 1 in place of a, you get the property we sort of proved above. You can generalize this for like a negative a also. So you get Dirac delta of at is equal to Dirac delta of t divided by absolute value of a. So this absolute value is because if you repeat the steps for like a negative a, so you sort of get this result, which is pretty easy to see. I hope this satisfied everyone over there, including the math majors. This probably wasn't the most rigorous way of doing it. It's not like a real proof. I'm using epsilons and deltas, but I think it suffices. Okay, another interesting one is the delta of this quadratic t squared minus a squared, where a is some constant. Let's say it's positive, and we can generalize later. So this thing has two zeros. One's at t equals a and the other is at t equals negative a. So we sort of need to break apart those 2 points, because everywhere else the integral will be 0. Integral from t minus to t plus dt f of t delta t squared minus a squared. Okay, what we can do is sort of localize around those zeros. So the first 0 is a negative a minus delta negative a plus, sorry, it's not delta, it's epsilon, my bad, dt f of t delta t squared minus a squared for some epsilon greater than 0. Epsilon is arbitrarily small, plus second 0 is at positive a minus epsilon a plus epsilon dt f of t delta t squared minus a squared. Okay, we want epsilon to be sort of in this range. The thing is, t squared minus a squared can be factorized as t minus a and t plus a, difference of squares formula from algebra, which is basically t plus a times negative 2a when t approaches negative a. It's t minus a times 2a when t approaches positive a. How do I get this? It's because of Taylor series. So it's a Taylor expansion around the points negative a and a. So t squared minus a squared is approximately equal to t naught squared minus a squared plus derivative of t squared minus a squared with respect to t at t is equal to t naught times t minus t naught. That's the first term of the derivative, which is clearly valid because we're in a really arbitrarily small neighborhood of the zeros. And since our case t naught is equal to negative and positive a, the first term just goes to 0. So we'll have t squared minus a squared is equal to the derivative, which we just plugged in. So derivative of this guy was, I believe, 2t at t equals t naught times t minus t naught. So if you expand it around, say, negative a, you're going to have negative 2a like here. If If you expand it around a, you're going to have the second term here. So you get these. And why is this helpful? Because as epsilon approaches 0, this integral from negative a minus epsilon to negative a plus epsilon dt f of t delta of, well, the first guy around negative a, we can expand using Taylor series to get negative 2a t plus a inside the delta plus integral a minus epsilon a plus epsilon, I believe, dt f of t delta 2a t minus a. So you sort of simplify this out using the formula we sort of defined on the previous page of, you know, scalar times the argument. Using that formula, this formula basically, we can simplify this out to get t minus t plus dt f of t delta t squared minus a squared is 1 over 2a f of negative a plus 1 over 2a f of a. So you sort of want to, if you write this in a case-wise manner, this is just the case when negative a and a are in the range. If you want to write this case-wise, we have 1 over 2a f of negative a t minus negative a t plus for this, 1 over 2a f of a when just positive a is in the range, and when both are in the range we have 1 over 2a f of negative a plus 1 over 2a f of a when t minus and negative a and a are both in the range, and 0 otherwise, obviously, if none are in the range. None of the zeros are in the range. This sort of looks like two spikes going to infinity on the graph. You graph the delta of this quadratic argument out. Sort of looks like this. Okay. If you want to generalize, just put an absolute value. So this was for a is greater than 0. To generalize, put an absolute value, and the absolute value sort of creeps in because of this, because of using this formula here. Because we would do the same steps for a general a, sort of expand it around or take a arbitrarily small neighborhood around those zeros, expand using the Taylor series, and then when you expand it out, we're going to write this delta term as this. So you have this absolute value included for the general case, which extends out here for these individual cases. One nice thing I can do with this formula is if you have t minus t plus dt e raised to t, if f of t is e raised to t, my delta is t squared minus x squared. This just becomes by the formula 1 over 2x. I mean, if you want to write the absolute value, write it, but I'm just saying x is greater than 0. E to the negative x plus 1 over 2x e to the x. If you expand this or notice what this is, we have 1 over x hyperbolic cosine of x. So this is probably a nice result which you might want to use. Again, absolute value in the case for a general x. Okay, so what we can do is, if this was just for a quadratic function, what if we have a general function, I don't know, g of t? Well, what we can do is we can write g of t as g of t sub I plus derivative of g with respect to t, evaluate t is equal to t sub I. This is using the Taylor series, the first term of the Taylor series, first two terms of the Taylor series. And this is for t is equal to t sub I plus epsilon, for epsilon which is arbitrarily small. Okay, what are we gonna do now? Well, since we are assuming t sub I is a 0 of g, 0. This is just derivative of g with respect to t, evaluated t is equal to t sub I times t minus t sub I, which makes the delta of g, so g of t, delta of derivative of g of t with respect to t at t sub I times t minus t sub I. Since this derivative at a point is just a number, it's a constant scalar, we can sort of divide it out using the property above here, the property with this bullet. We divide by the factor, absolute value of the factor, derivative of g with respect to t in the denominator at t is equal to t sub I. This is an absolute value, t minus t sub I, delta of that. But this was for 1 0. This guy had 2 zeros. We don't know how many zeros it may have, so let's just sum for all zeros that are included in this range. So I goes from whatever 1 to n, where like n is the number of zeros of g of t in the range of t minus 2, say t plus, in this range. So, yep, this is a pretty nice generalization, because again it's hard. This kind of works for polynomials, but it's kind of hard to find zeros of polynomials of higher and higher order. May work for like sines and cosines, but this will just be an infinite series unless you restrict the domain. So I don't know, I just wanted to share this to you guys. Might find it useful, you may not, but it's a nice property. Okay, let's talk about some integral operators on the Dirac Delta function. So although we can't really like integrate and differentiate, but since it's like a distribution, if you look at it in terms of a distribution, a generalized function, these things are made possible just because of the motivation for introducing a distribution. I believe I explained mathematically in whatever terms I could in the last video what a distribution is. So let's say h of x is equal to integral from negative infinity to x of Dirac delta of t with respect to t. So this guy h of x is, I haven't given it a name yet, is just the area under the delta in the range that's specified here. So t tending from negative infinity to t equal to x. So if t is less than 0, x is less than 0, my bad, the range excludes t equals 0, which is the 0 of the delta in the normal default case. So h of x is going to be 0, because since if you don't include the 0 of the delta, it's going to be 0 everywhere, because delta of t will equal to 0. Well, as soon as x is greater than 0, the range excludes, well, at least includes, my bad, includes t equals 0. So when that's the case, h of x is 1, because the integral of the delta will be equal to 1, but just because of the definition. So the way I see it is h of x is 0 when x is less than 0, 1 when x is greater than 0, and this is precisely, we define this to be integral from negative infinity to x, integral of Dirac delta. And this was actually defined independently of the Dirac delta, but it just so happened the integral of the Dirac delta turned out to be this guy, which is the heavy side step function. I'll show you in a bit why this is called the step function, because if you're in the negative region it's 0, if you're in the positive region it's 1. So there's like this sort of a ladder structure going on here. This is my x-axis. This is h of x being equal to 1. This is h of x being equal to 0. So in the negative region it's 0, in the positive region it's 1. In the transition, which is happens at x equals 0, it sort of has an infinite value, or infinite slope rather. So the thing is, since h of 0 is undefined, really, like it can either be 0 1, there's like a jump discontinuity. We define by convention h of 0 to be h in the positive region plus h in the negative region over 2, the average of those guys, which turns out to be 1/2. 0 plus 1 over 2 is 1/2. And the reason for doing this is because when we get to Fourier series, and when we start describing square waves such as this guy, of which this guy, the Heaviside step function, is just a part or one unrepeated element, that's when you'll see that this guy, you construct this using a series of sines and cosines, is actually the sort of the average of the positive and the negative branch. So that's the reason for doing it. Again, it's a statistically convenient way thinking about this. Okay, moving on. Okay, so the derivative of the Dirac delta, we just write this informally this way. Again, I can't write a Dirac delta outside the integral, but again, thinking of this as a distribution and enables us to write this, take a derivative of this, although we can't really. It's like one spike, which is not differentiable at that point, but we can think of this as like taking the derivative of the delta sequence. So the popular delta sequence, the Gaussian sequence, say d over dt of n over square root pi e raised to negative n squared t squared. And the graph of this, because you know what the Gaussian delta sequence looks like, if you differentiate that, the derivative of that at some n value looks a little like this. It's sort of one spike here and then one spike from below. So sort of 0 here in magnitude, infinity here, negative infinity here, 0 here, sort of like a tangent, like a weird tangent curve, or like an inverse curve going on. So this is what we call the doublet spike. And of course, as n tends to infinity, as it should in the limit, this becomes more and more spiky as this gets closer. So let me define this. Integral from t minus to t plus dt f of t delta prime of t, which is the derivative of delta with respect to t. Again, I'm using Newtonian convention. I can use integration by parts. I can integrate the delta and while I differentiate f of t. So in the first step, just integrate, don't differentiate. Add those upper and lower bounds. Minus integral at those bounds of, well, now you differentiate f of t while you integrate the delta. So d of f of t with respect to t, delta of t. The first guy, as long as t minus and t plus are not 0, or are not exactly 0, it is going to be 0, because if you remember the graph of the delta function, it's like spike just at t equals 0. Everywhere else it was 0. So since we are at everywhere else, we're evaluating it everywhere else using this assumption in the bracket, the first term just becomes 0. We have the second term, which is negative t minus t plus dt derivative with respect to t of f of t, delta of t. This is, we can write this as in a sort of a definition, is negative f prime of 0, t minus and t plus, as long as 0 is in that range, and 0 otherwise. So again, this is using the definition of Dirac delta because the derivative of a function f, as long as it exists, and it's a good assumption to assume it exists because f was like continuous and like well behaved. So f prime is also a function. So you just evaluate at that point using the first property of the Dirac delta that I proved in the last video. So this means that t prime t plus dt f of t delta prime of t is just going to be negative t minus t plus dt f prime of t delta of t. Yep, we just get a negative sign. We change the derivative from the delta to the function itself. A way to generalize this is as follows. Again, it depends on what kind of generalization you want, but nth derivative of Dirac delta of t is basically minus 1 to the n, because if you see the pattern, the minus will keep alternating. Nth derivative of f at 0, assuming it exists. Again, we want f to be continuously differentiable, so we assume that f of t is Cn, which is n times continuously differentiable. It should exist, it should be differentiable n times, which again is a valid assumption in whatever case you're working on. So I hope this video helped. I covered, I think, the basic properties of the Dirac delta. Please like, share and subscribe to my channel, guys. Recommend to your friends. Spread the word of Gamma Di Gamma in the math community. In the meantime, stay home, stay safe, keep doing math, and stay tuned for more content. Peace out.